This video is the third installment of 3 videos covering translations of functions. So in this video, we're going to cover horizontal and vertical reflections and identifying symmetry. In previous installments, we did horizontal and vertical shifts, and in the second video of the series, we did the horizontal and vertical expansions and compressions. Let's talk about reflections. You get a reflection of the graph of a function when you include a multiplier of -1 either outside the function or inside the argument. And if you want to see reflections in action, it works the best if you pick some kind of a function that doesn't have symmetry, which we're going to talk about, but you'll see what I mean when we look at some examples. So let's hop over to the calculator and take a quick look at a reflection in action. We want you to notice that if you put a minus sign outside the argument, you get a reflection across the x-axis. And if you put the minus sign inside the argument, you get a reflection across the y-axis. Now, some functions don't change appearance when they are reflected, and that's because they have symmetry. But we're going to use an example initially that does not have symmetry, and we're going to use that to showcase what we're talking about here. Let's take a look. So I have as my untranslated function, my f of x, in y sub 1 there, I have square root of x. And the domain of that function is non-negative reals, and it's going to graph in blue. And then I have in red y sub 2, which is the square root of negative x, or the opposite of x. And if you think about the domain of that function, it is from negative infinity to 0, with a square bracket on 0. And then in black, y sub 3 is the opposite of the square root of x, and that is going to produce a reflection across the x-axis. So again, to recap what you're going to see, the function in blue is the original function, the function in red is a reflection across the y-axis, and the function in black is a reflection across the x-axis. I think we can graph these just using a standard zoom, and that should be sufficient. So there's the original function, there's the reflection about the y-axis in red, and there's the reflection about the x-axis in black. Now, if you take certain functions that have symmetry and you reflect them, the graph looks the same because they have symmetry, but the vast majority of functions do not have symmetry. And what we want you to be able to do is not plug in something on your calculator necessarily and graph it to see, what you get. I mean, there's certainly nothing wrong with that, but for this example, it's kind of along the lines of what we saw in the previous videos. We're going to give you a function, and we're going to ask you, hey, what do you see? How do you read the graph? Let's look at an example of that. So in some respects, this is kind of the capstone example here with regard to reading the graphs. I mean, I have other examples in the video, but this is kind of the meat and potatoes here. So this has a combination of horizontal shifting, vertical shifting, reflection, scaling, all of that in one. And what we're asking you is to look at the graph and tell us what you see. So there's a few things you want to pay attention to as you go about this. You want to look at the domain, you want to look at the range, you want to see if the locations of anything has changed. In other words, extrema, for example, where the graph crosses the axes, where is it increasing, where is it decreasing, all of that stuff. And if you practice a little bit at this, it's really not that hard, and you'll be able to answer this type of a question on an exam, for example, very easily. Let's take a look at our graph. So on the left, we have our original piecewise linear function, and on the right, we have a changed version of that. And so we're asking you, hey, why don't you pause the video and take a careful look at those things that we were talking about. What's the domain of this function? What's the range? Has it been scaled either horizontally or vertically? Has it been reflected? So on and so forth. Think about it for a second, and then we'll showcase the answer. So let me run through what I'm noticing here. First, I'm looking at the function on the left, and I notice once again that the domain of this function goes from -8 to +8 on the x-axis. I look at the function on the right, and the domain goes from -6 to +10 on the x-axis. So clearly there has been a horizontal shift because the domains have the same length, right? -8 to +8 is a length of 16, just as -6 to +10 is a length of 16. So since the length of the domain hasn't changed, I know there hasn't been any horizontal compression or expansion. And it looks to me like all we have is a horizontal shift 2 units to the right. You can confirm that by looking at the center of the function on the left. The center of the function, so to speak, goes through the origin. And the function on the right, it goes through the point 2, 3. And so that brings me to the next thing. It looks like the function on the right has also been shifted vertically. Because when I'm starting to look at it, I notice that the features, like for example, the endpoints, which are on the x-axis on the left, they are raised by 3 units on the right. And so it looks like a vertical shift of 3 units has taken place. Now, as far as the range, I'm looking at the function on the left. The range goes from -4 to +4 on the y-axis. That has a length of 8. But the function on the right, the range goes from -3 to +9 on the y-axis. It has a length of 12. And if you take the ratio 12 divided by 8, you get 1.5. And so that looks like a vertical scaling has taken place. The function on the right has been multiplied outside the argument by 1.5. Now I'm noticing something else. I'm kind of getting ahead of myself a little bit here in the video, but the function on the left happens to be an odd function. That means that it has a special kind of symmetry. And I'm noticing that the function on the right has clearly been reflected in some fashion. Now you could actually describe the reflection a couple of ways. You could say reflected about the y-axis or reflected about the x-axis. You get the same result because the original function we started with was odd. So if I'm going to combine all of these things together, I'm noticing again, horizontal shift 2 units to the right, vertical shift 3 units up. I've been scaled by a factor of 1.5, and it looks like a reflection has taken place. Let's put that down. Now I described the reflection here as being across the x-axis. You'll see why in a bit, but again, because of the symmetry, it really doesn't make a difference how you describe it. But I put down here on this slide everything that we talked about, that we were just looking at. And so if you put all of those things together, what do we have? Well, let's take a look. This is one way of expressing this right here. You could also write it a little bit differently depending on where you want to put the 3, the vertical shift. So once again, we have a vertical shift of 3 units. We have a reflection. We scaled it vertically by a factor of 1.5, otherwise known as 3/2. And we translated 2 units to the right. And so hopefully you'll get some practice doing this. We have some on the mock exam for you, and I think you can find some in the text as well. So please do look carefully at this, and then let's talk about symmetry. So we really have 2 kinds of symmetry that we're looking for. And again, it's kind of helpful to remember that the vast majority of functions don't exhibit symmetry. But there are a few that do, and it's worth knowing how to recognize that. So notice that when you're testing for symmetry, both of the instructions begin with when f of minus x equals. And so the implication that would follow from that is that when you're testing for symmetry, whether it's using function notation with f of x or whether it's using y or some other letter, it doesn't matter. The idea is you go to the function or the expression, and you're going to replace all of the independent variables with the opposite of that independent variable. So in the normal notation we have x comma y. That's an ordered pair. And it's understood that x is the independent variable and y is the dependent variable. So the idea is you would go into your expression or your function and you would replace all of the x's with the opposite of x. And then you're going to simplify to the extent that it's possible and compare it with what you started with. And so if you end up with the original function, f of x, that means you have even symmetry. And if you end up with the opposite of f of x, that means you have odd symmetry, or origin symmetry as it's called sometimes. And if you have neither one of those, then you have no symmetry. And so we want to showcase a couple of examples of that, but let's go and take a look at something here. Now when you look at the graph of an even function, it has what we would call y-axis symmetry. So in other words, the y-axis is kind of like a dividing line, and if you were to take a graph of a function that has that type of symmetry and you printed it on paper, and you folded it so that the y-axis was the fold, you would find that the two halves would coincide exactly. And that is what we call even symmetry, or an even function. And so if you're looking for some examples of functions which are even, you can graph these for yourself, and you can see x squared is an even function, x to the fourth is an even function, x to the sixth is an even function, and reciprocals of those are also even. And there are many, many others. We're not trying to make you an expert on even functions, but we just want you to know it when you see it. And so if you look at the graph that's there, that's also an even function. And you can see that if you were to print that out and fold it so that the y-axis is the fold, the two halves would coincide exactly. And so if you try to reflect that function by putting minus x in for the argument, you'll find that the reflection across the y-axis looks exactly the same as the function. It doesn't change because it has that even symmetry. What about odd symmetry? Examples of odd functions would include x to the first, in other words, right? X cubed, x to the fifth power, 1 over x cubed, and so on and so on and so on. And you can see that the graph that I've put over there at the right is also an odd function. It has that origin symmetry, if you will. And if you wanted to test for that, you would take the formula for that function and you'd put in minus x as the argument, and you'd find that it's the same as the opposite of f of x. That's odd symmetry. Now, typically what we want from you is we want you to know it when you see it, but also to be able to check for it. So in other words, if we give you some function and we ask you, hey, is it even or odd or neither, our idea is that you would put in minus x for the argument and you would simplify and see what you get and show your work, of course. And then it should be pretty clear. Now, there are some patterns kind of lurking here in the background, and I'm going to talk about that in a second, but let's look at a couple of quick examples of something you might find in the text. Now, if you're wondering how would they go about asking regarding symmetry in the book, it's a couple of ways. You can be asked as you see at the top here. So if you look at problems 25 and 26 and 27 and 28, the instructions, which are not visible here, but they're stated on the previous page, they're basically asking, among other things, that you would tell whether the graph has even or odd symmetry or no symmetry whatsoever. And so you can be asked graphically to look at something, and you can also be asked algebraically, as you can see down below, problems 33, 34, and so on up through number 44. So in other words, something is provided in algebraic form, and we ask you, hey, what do you see here? And so we want to look at a couple of quick examples of the algebraic variety, since that's the most germane with regard to what we're talking about here. So let's say we presented you with a function like the one you see here on the screen, and we asked you to test it for symmetry. So we want to know, is this function even or odd or neither? And we want you to show us algebraically how you know. So again, the idea would be that you take this function and you replace the argument x with the opposite of x. And then you simplify and you see what you get. Keep one thing in mind. Now, for many people, when they're getting started with this, it's sort of helpful to ask yourself, what would the opposite of f of x actually look like if I had that? Because sometimes you'll see people work a problem like this and they end up with the correct result, but they don't recognize what they've got. Another thing that's very good to remember is that when you have a rational expression, as we have here, and you have a minus sign floating around, you have a certain amount of license regarding where that's going to go. So you can put it in the top, you can put it in the middle, you can put it in the bottom, and any one of those is fine, but it can change the way things look. So like in this case here, for example, if you're looking at the opposite of f of x, and you understand what that means on a practical level, you've got a minus sign floating around out there. Can you bury it and make the expression simpler? And actually you can. And so you can take the minus sign that's on the outside of the quantity and you can bury it in the denominator, and it changes the direction of the subtraction from 4 minus x squared to x squared minus 4. I'm not saying you have to do that, but sometimes it comes out that way, and it's helpful to know that a minus sign floating around can cause something to change the way it looks. Anyway, let's take care of this particular problem. What is f of minus x going to give us? So now, when I replace x with the opposite of x, or minus x, however you choose to call it, That's the expression I get down there at the bottom, and now I need to simplify that. Now hopefully you know the law of exponents says that if you take the opposite of x and you square it, that's the same as x. So you get the following. And so it happens in this case that you don't actually get minus f of x, you get f of x. And so this function has even symmetry. Now, if you happen to know the patterns that are lurking in the background, you can answer this kind of question more directly using something like that. But let's look at one more example of this type of problem. Let's say we asked you to assess this function here, find out whether it's even or odd or neither. And so again, the idea might be helpful to write down what does the opposite of g of x look like, because that is certainly a possibility here. And so just in case we get that result, there's the opposite of g of x. So let's test this particular function here for symmetry. So I plug in minus x for x, and now I need to simplify. And so as you can see, when you put in minus x and you cube it, it's the same as the opposite of x cubed, so that 4 times quantity minus x cubed is the same as negative 4x cubed. Likewise, minus x quantity squared would be the opposite of x squared, as you see there. And if you take x and you take the opposite of it, you're going to get minus x. And so when you compare the expression that we obtained with what we started with and with the opposite of g of x, it doesn't match either of them. And so in this case, this function does not have any symmetry. It's neither even nor odd. And so there's my answer. And look carefully at what I wrote. It should be clear why everything is what it is. And if it's not, then feel free to drop me a line. But one more thing. I'm not going to show it in this particular video, but it turns out that there are some patterns lurking behind the scenes. And so if you're looking for an example of such patterns, if you take odd functions and you add them together, the result that you get is again odd. Likewise, if you take even functions and you add them together, the result that you get is again even. And there are many other such patterns. And so that's nice to know. If you can show, it's very easy actually to show. You can establish a lot of different patterns with regard to symmetry. But anyway, hope this has been helpful. And again, if you have any questions, feel free to drop me a line. Otherwise, go on to the next video.